It's almost a little flat, and if it's not flat, it would be one of those what we call bimodal distributions, or the two humps of the scores. Top score, it's actually in the 90s here. There was a 100 on the exam, so top end on at 100. The lower scores here were in the 40s. And so you can sort of see, here's the 60s. There's one of these two scores, 61, I think it was, very close to the 60. And then there was another one, it was 69 or 67, an odd numbered high 60s score. So there's sort of this really sort of a breaking point between those two peaks. And so I finished these up last night, came in and recorded scores and sort of, in the evening last night after dinner. And I've been trying to, since then, think about how we might make adjustments if we need to this. The score here alone doesn't bother me so much. I was clear with the first exam. Average between the two exams being about a 75. That's not terrible. But what I'm a little bit, if you will, worried about is the 7 scores down at this end. I don't necessarily know if it truly reflects your understanding of the material. We could sort of do a shift, but notice we do have scores way up here, and so a shift tends to start to put things up at the over 100 range, and I don't really want to do that either. So what I think I'd like to do is not adjust this exam at all, but adjust the scale for the grades at the end of the semester, once we put in together the two exams and the homework and the final together. So I'll adjust that scale, maybe stretching it out a little bit. I don't know exactly where they're at yet, but say, for example, BCs might drop down to something in the 75 range rather than the 78, and C's down maybe around the 65 kind of range rather than the 70, and then the passing grades down into the mid-50s kind of range. Just stretching out that scale rather than trying to adjust individually on this exam. But overall, like I said, a little bit of a worry down here. This is looking very nice. The average doesn't bother me a whole lot. And if you will, as we start to talk through it, the recognition of at least the approach that should be used for various proofs by the class as a whole, a few individual exceptions, was very, very encouraging from my perspective. So let's start our day then by going through and talking a little bit about the exam, what should be done, if you will, if you didn't get it, and sort of a little bit more about how I scored and assessed each of the problems. So first, square root of 3 is irrational. Every one of you started this one with contradiction. Proceed by contradiction. Yay! Right? That's the key way to show something like the square root of 2, or in this case the square root of 3 is irrational. And that was a third of the points alone. The words proceed by contradiction. That's a third of the points because you've recognized the style of proof, the argument that should be needed. There were a few issues with proceeding beyond the following. So you assumed that it was rational, and you wrote it as say A over B, whatever variables people used, and then squared it. So most people got to that point, and I think getting to that point in the argument was a little over half, so 7 out of the 12 points for assume or proceed by contradiction, write square root of 3 as a rational number, where A and B are integers, and get to this point. And here's where some of you could sort of see, I could sort of see where you were trying to remember rather than think through, trying to go with rote recollection rather than what was the process and trying to think through the process. You recognize that you wanted to count factors of things. And here, we're wanting to count the factors of 3. So you'll count how many factors of 3 are there in A. Give that a number, n. Then A squared would have twice that many factors of 3 in it, an even number. You could do the same for B. B has some number. B squared has twice that many, also then an even number. So that 3B squared would have the even number from B squared plus one more 3. That's an odd number of 3's on the left-hand side, but an even number on the right. And that's the contradiction that you're arriving at. There were a few people that that used the other approach. That used the other approach where you wrote this as A over B in reduced form, and then you noted here that 3 divides the left-hand side, so it must divide the right-hand side. And if 3 divides A squared, then it must divide A, because 3 being prime can't be broken up into pieces. And now 3 is divisible here, and you work on getting the fact that A and B were not in reduced form. They shared a common factor. Anybody want to see more depth on that? That was just a broad overview. We can look at it more specifically. Any one of the problems we go through, I'm going to give sketchy kind of discussion. If you want to see thorough or rigorous, let me know and we'll do that.
You did 9. 9.
Oh yeah, we're going to go through all of them.
Oh, I'm sorry.
Okay. Yep, we will. I just want to know on this one though.
Oh.
We're good? On this one? All right. Number 2, what does it mean to be an equivalence relation? Everybody got that one, I think. I actually think everybody got it. You need to be reflexive, symmetric, and transitive. Initially, I was thinking here that I was going to, in part A, if you didn't write out what reflexive, transitive, and symmetric meant, in the end I decided to not do that, because in part B, all of you started, here's what it means to be reflexive. So I think, okay, we're good there. So showing that A plus 3B being even makes A and B being related is an equivalence relation. So quick notes. I know A plus 3A is even, A is related to A. That's short. A lot of you went through more in-depth approaches. Several of you did things like taking the case where A is even and then where A is odd. Right? In that case, while it works totally well, it also takes a little bit extra time, and that might have been an issue where time became an issue for you. There tended to be a few, smaller number, but a few people that had issues with showing symmetry and transitivity. Because recall that symmetry, if AB is an element of R, then BA is an element of R. And a lot of people had this as and, this and this. It's not both there. It could totally be the case that AB and BA are not in the relation, and it still be symmetric. What we need to have is, if this one's there, then that one must be there. And so you assume that A plus 3B is twice some number, 2k, and then you need to show, so assume and show B plus 3A is twice, say, some other number. Many of you used the approach, or at least we're trying to use the approach that we talked about as one of the methods for this in class, where we can sort of add these up and then solve for L and say, hey, now I know what L must be, and then check. Does L work? Right? Does that choice of L work? And so say 2L equals this, blah, blah, blah. A little bit of algebra later, you get B plus 3A. So it's a two-step process. You say, hey, let's assume this is the case, find out what L is, and then go back and verify it. The issue that some people had was you assume both of these. And then say, hey, you know what? If we assume this one, look, it is. And then when you assume that you have what you're trying to prove, then it's very easy to prove it. It's just a statement. It's true, I assumed it. So if you use that approach, what you would do is you'd take both of these, you'd assume this one, that's true, pretend this one is true, figure out what L has to be, then go back and verify it. There are other ways you can do it, and some people did the following. So I take, for example, start here with this one. I'm going to rewrite it. A plus 3b is 2k. And our goal is to get, eventually, something like this. Multiply both sides here by 3. Take this 9b and break it up. And now take the 8b and push it over to the right-hand side. Reorder these just because we can switch the order of addition. 6k minus 8b, and now that's twice 3k minus 4b. So this number is now an even number. So there are many ways you can go about this. That would be my description here, and this one, two distinctly different ways you go about it. For transitivity, transitivity turns out to be much, much, much easier in this case. If you assume A and B are related, and, so here's an if, A and B are related, and B and C are related, then A and C are related. What you'll do is, from this, you get A plus 3B is twice some number, and B plus 3C is twice some number. So both of those are assumed, they're coming out of the hypotheses right there. And now add these up. A plus 4B plus 3C is 2K plus 2L. Bring the 4B to the right-hand side. 2K plus L plus 2B. With a little factor in there. And now we get A plus 3C being an even number. So there were a few issues with the symmetry and transitivity for people, but most got the reflexivity right. Anybody want to see more detail in any of those? All right. In terms of scoring there, I'll read my sketchy handwriting here. Oh, I didn't. There's basically a point for trying, and then 3 points for each of these: reflexivity, symmetry, and transitivity. Right? So if you got one of them verified correct, that was 4. You got 2 of them, that's 7, and all 3 of them for the 10 points. Let's see, number 3, give an example on that 3-letter set that's reflexive and symmetric, but not transitive. Many people, I won't say everybody, but many people use the picture to start with, so I'll do so. So there's our 3 points, and virtually all remembered that to be reflexive we needed these loops, so that A is related to A, B is related to B, and C is related to C. More than one left it at this and said, all arrows go both ways, and it's not transitive because there's no triangles, if you will. But note, it is transitive. Every time A is related to B and B is related to C, A is related to C. Every time over there. Rationale being the hypotheses here are met. There is no, well, the only way we could meet these hypotheses is for A, B, and C over here to have all been the same values. A is related to A, and A is related to A, so A is related to A. Yeah, that would be the case. So this is reflexive, but it's also transitive, and it's symmetric. So it's all 3 of them there. Some people have this one. Again here, notice, nice and symmetric, as well as the reflexive as well. But this one also is transitive as well. A is related to B, sorry, C. A is related to C. C is related to C, so A is related to C. A is related to C, C is related to A, so A is related to A. Every time we get the first 2 over there, we get the third one as well. In order to end up being non-transitive, you need to, in essence, make 2 legs of the triangle without the third one. So now, every arrow is a double arrow, but we can go from A to C and C to B, but not A to B. So there would be an example of a non-transitive symmetric reflexive one. Further details there? That was an 8-point one. Right, 8-point problem. 3 points for each of the 3, well, 3 points, last one being 2. 3, 3, and 2 for getting correctly described either reflexive, symmetric, or non-transitive. You've got 2 of those 3 correct, you got 8 or 6 out of the 8 points. So if you had something that wasn't transitive, was reflective, but turned out to be non-symmetric, that was 1 of the 3 being wrong, that would have been a 6 out of 8. Questions there? Fair enough. Number 4. I was very happy with numbers 4 and 5. Thought of them, think of them sort of as a pair here, in that I think, with the exceptions of a couple people on 5, you guys as a whole, the class recognized these are induction kind of problems. We're going to induct on the value of n. Quickly in number 4, just to set it up. The base case, just plug in n equals 1 and show 1 is equal to 1. Yay, rah, everything is nice there. So we would assume this. Here's our inductive assumption. We're going to assume this, and then we're going to show that. Simply getting to that point, so if you set up your argument as proceed by induction, showed the base case, made this assumption, and declared this is what I need to show, getting to that point was 8 out of the 12 points. Right? Basically saying, roughly, you're at a passing level if you can understand 2 things: when induction is used, and how to at least get it to the point of showing everything except for that inductive step. At this point, to get to those remaining third of the points, what we do is we need to verify this is the case. And the way to do that is to note, and I'll do a little bit of sketch here, right there sits our inductive assumption. I can replace this with that over there. And so we probably have another line where we said, hey, this stuff, 1 times 1 factorial, plus all the way out to the k plus 1 times k plus 1 factorial is equal to this bit, minus 1. That's there. That's this stuff. And then add to that k plus 1 times k plus 1 factorial. That's this. So this piece is right here, and this stuff is now right there. And now, here's where we want to go. That's what we want to look like. Notice it's got a minus 1 at the end, so let's put the minus 1 that we have here at the end. And then the other 2 things each have a k plus 1 factorial as a common factor, if you will. There it is in each of those. Factor it out. I'll factor it out and put it on the right-hand side of the factoring process. What we're left with is a 1 here, and a k plus 1 here, and then the k plus 1 factorial that we factored out. Here we now get a k plus 2. K plus 2 times k plus 1 factorial is k plus 2 factorial. A factorial times the next larger integer is the next larger integer factorial. And so this becomes k plus 2 factorial minus 1. Exactly where we want it to be. Check. Or box, or QED, or whatever. Questions on that argument? Like I said, bonus, or bravo as a class, bravo, for recognizing we needed to use induction on both this one and the next one we're going to look at. The next one is the division problem, 6 to the n minus 1 divisible by 5. Okay? All right, so again here, you'll proceed by induction. You'll show the base case. In this case, we want it for all positive integers. And so when n is 1 would be the base case. 6 to 1 would be 6, minus 1 is 5. 5 equals 5 times 1, so it's divisible by 5. And then we assume 6 to the k minus 1 is 5. Here was a common error, common in the sense that maybe 4 or 5 of you made this error. While we like to use k as our arbitrary integer, if it's used here, we don't want these two to be the same because they are likely to be different numeric values. And so if you like k over here, then use maybe m here instead. So we get to assume that 6 to the k minus 1 is equal to 5l, and we need to show 6 to the k plus 1 minus 1 is equal to 5m for some m. That it's divisible by 5. That's what it means to be divisible by 5, right? All right. What we'll do is take 6 to the k plus 1 minus 1 and write it as 6 to the k times 6 minus 1. There are a couple of ways you could do this, by the way. At this point, we could use the fact that we know something about 6 to the k and simply write it in here. 6 to the k minus 1 is 5l, so 6 to the k is 5l plus 1. And we can write that in here. 5l plus 1 times 6. Distribute through 5l times 6 plus 1 times 6 minus 1. 5l times 6 plus 5. Factor a 5 out of there. The alternate approach would be to take this 6 and rewrite it as 5 plus 1. And then distribute the 6k through, 6 to the k through, and you'll get a 6 to the k times 5. Hey, that's divisible by 5. Plus 6 to the k times 1. 6 to the k times 1 minus 1. There's the other divisible by 5 piece. So you do that replacement or use of the assumption at that point. Maybe I'll write that this way. And now you've got two pieces, each having a factor of 5 you could factor out. Okay? So two different approaches there, either one of them would work. Questions there? Again, roughly, getting to this point was about 2/3 of the points, the rest of it being the final third. Questions on either of those two inductions? As I said, overall, I thought that you guys did very well on the induction problems there, on those two at least. Number 6, very pleased to see that this one went well. It was one that we had talked about shortly before the exam. We were in class maybe the day before or 2 days before the exam. Things went well there. There were a few, 2 or 3 people maybe, that I could tell were trying to produce this from memory recall rather than making their way through the argument again, and had a few sort of careless errors that caused issues. All but a couple recognize here again this would be a contradiction argument, and so we would proceed by contradiction. Assume x is rational, y is irrational, and xy is rational. Idea here being, the official statement was something on the lines of P and Q implies R. X is rational, Y is irrational implies XY is irrational. That's the statement we want to prove. The negation of this would be P and Q and not R. Logically equivalent that way. And so we would assume this, and now we arrive at our contradiction. The way we're going to do that is, x being rational, it can be written as a quotient. In this case, we know a and b are non-zero. The original problem says x is not 0. So that makes both a and b non-zero. We'll write xy as maybe m over n, where here n is non-zero. That makes sense. And then we write xy is a over b times y. It's also m over n. Invert and multiply. mb over na. Here's where the bonus of a being non-zero comes into play. You can divide by it. And now we've written y as a rational number. That's the contradiction. Questions on that one? All right. And then we get to the final three problems. I think of these final three problems, first I'll say the first six seem to go pretty well for most. And that's, you know, if the exam was long, you guys got through that without too much issue. 7 through 9 is where there were a few issues. In particular, I would argue 7 and 9 were probably the two hardest problems on the exam. 7, once we start to see 7, I think several of you are going to maybe kick yourselves a little bit. Where it became an issue for people, I think, was the use of both x and n in it. There were a number of you that were trying to induct correctly, we should be inducting here, but inducting on x, and we want to induct on n. I tried to give a hint to that by the wording of it. For a fixed value of x, x isn't being allowed to change. And show that that's true for all positive integers n. It's the n where that the universal quantifier is being used there. So we're inducting, remember, induction works on a for all n in the natural numbers kind of situation. And this statement is for all natural numbers n, that statement is a true statement. Let's take a quick look at it then. So for all n in the naturals, and fixed x greater than -1, show that 1 plus x to the n is greater than or equal to 1 plus nx. We're going to induct on n, so n equals 1 is our base case. 1 plus x to the 1 is equal to 1 plus x, which is greater than or equal to 1 plus 1 times x. Yep, check. Assume 1 plus x to the k is greater than or equal to 1 plus kx. Show 1 plus x to the k plus 1 is greater than or equal to 1 plus k plus 1 x. Here we have an inequality. Just like when we have an equality doing an induction, we start with one side and we work to the other. By factoring it in that way, all of a sudden we see information about our assumption. And so now we can apply our assumption here. Here's a number times this value. It's going to be larger than that same number times this value. So this is greater than or equal to 1 plus x times 1 plus kx. 1 plus x times 1 plus kx, we can expand that out. 1 plus x plus kx plus kx squared. You might at this point recognize 1 plus x plus kx, if you take that last two terms and factor the x out, you get exactly 1 plus k plus 1x. So there's what we want. What we have on this instead is an extra term, a kx squared term. But since x squared will always be non-negative, and k is one of our induction values, it's a natural number, it's non-negative, this quantity is a non-negative quantity. So this is all greater than or equal to 1 plus k plus 1x. And I'll put that here, since kx squared is greater than or equal to 0. And that's what we wanted to be at. So now we're at, there we are, we're done. There were those